So the topic for this last session here is slightly more sophisticated models than we have seen so far. So we're actually going beyond just Bayesian linear regression. And we'll be looking into slightly more complex models. So just to motivate things a bit, our starting point. So we heard a bit yesterday about factor analysis models. Both Celia and Andrew introduced them briefly, and I'm also just going to do it here, but more to motivate what we are going to look at afterwards. So with a factor analysis model, you have a model specification given by the graphical structure up here. So you have some latent factors, in this case here 2, that are assumed to be a priori independent of each other. And then you have some observation variables down here. We have 4 of them in total that assume to follow a normal distribution condition on the latent factors that you have up here. And the way that it's interpreted is that the model that you have here, the data that you observe, is generated from these independent factors here, plus some additional observation noise that are being added. And with this type of model class, there are some relatively simple algorithms that we can use in order to learn the model parameters. So that would be the mu that you have here and the weight matrix, the factor loadings connecting the factors to the data that you have. And once we have that, we can use this model here to, for instance, calculate for a given data sample here spanning these 4 variables that we have down here. We can calculate a latent representation of it, and that could then be a latent representation that may tell us something about the data that we have at hand. So we are using it to gather insight into our data, but we could also use it as a sort of intermediate representation for downstream analysis tasks that we could be interested in. So that's sort of some of the main features here. And the good thing is that we have sort of a nice, simple model that is interpretable, it's easy to understand, and it allows us to compress data into a low-dimensional representation that we are basically in control over. We can decide the number of dimensions that we want to have. The bad thing from our perspective is that the model is also very restrictive. With the standard setup that we have up here, sort of in its specification up here, all the distributions are assumed to be Gaussian, and we assume that there is a linear relationship between the latent factors that we have on top and our observations that we have down here below. So this also puts some limitations on what kind of data that we can actually model with this type of model, but also what kind of expressive representations that we can find from the data that we have at hand. So using this sort of as a departing point, we would like to look at a more complex or expressive model class. In this case here, a so-called variational autoencoder. And in terms of model structure, if you look at it from a graphical representation, it's very similar to the factor analysis model. Sort of if you mentally unfold the plate notation that you have up here, then you have a collection of data points in total, and for each data point you have a set of latent variables. So Zi here is a vector, a collection of latent variables, and Xi, again in boldface here, is a vector of observation variables that you have. And then you have a distribution between the Zi's and the Xi's, and that distribution is parameterized by some parameters omega that is placed outside this plate here because it's shared between all our data instances. And in these standard setup with these types of variational autoencoders is that we have isotropic Gaussian distributions over the latent variables, so they are assumed to be independent, meaning that we have here just a diagonal covariance matrix for them. And then we have a likelihood function connecting the Zi to our observations that can be parameterized by a deep neural network model. So you basically have a great deal of flexibility in the representation that connects, or the function that connects the latent variables here to the observations that we have. And this deep neural network model that you have can be used to parameterize, in this case here, on this example here, a Bernoulli distribution. So it could, for instance, provide the logits for the Bernoulli distributions, where we assume that we have a collection of binary random variables, each of which follows this Bernoulli distribution. So the reason why we have chosen this is just to again emphasize the difference between our departing point, which was the factor analysis model, where we assumed a Gaussian distribution. The neural network model that we have connecting the zi's and the xi's is also referred to as the decoder network, and we'll see shortly why that's the case. And then just to make things easy here, we are not going to put this into a fully Bayesian context. We're just saying that we are looking for some parameters, omega here, that we can optimize in order to find a model structure that fits well with our data. So this is the setup that we have here. And what we would like to do is to be able to calculate a posterior distribution over Zi for each of our data points. So you should imagine that you have a data point I, and for that data point I represented by xi, you want to calculate a posterior distribution over Zi. And for doing that, we go through Bayes' rule once again, at least in principle. So here we have the specification of Bayes' rule. This is getting a bit complicated by the fact that we have a potentially very complex neural network that provides a decoder network between the zi's and the xi's. So the normalization constant that you have down here will not be tractable to compute. So instead we resort to our favorite tool, variational inference. And our initial idea here is to define a variational distribution over these latent variables here for each of the set of latent variables for the data points that we have. Each of these distributions here having its own set of variational parameters that we want to optimize. And this is sort of what we have tried to indicate up here with a dashed line, that we are sort of moving in this direction here, and we are have this variational distribution over the Zi conditioned on xi. So this is sort of our initial plan. And the way that we want to sort of push this initial plan a bit further is that we are formulating our elbow, so our evidence lower bound that we've looked at several times today. That's given by this expression up here. And again, we have a product up here, one for each over each of the data points that we have in our data set. Let's assume that our variational distributions for each data point is just Gaussian, with that is parameterized by a mean vector and a covariance matrix. So if we, for instance, assume that we have a d-dimensional latent space, then we would have a d-dimensional vector Zi here, and we could have a diagonal covariance matrix here, also consisting of d component, one for each of the latent variables. If that is the case, and we assume sort of also putting in these rather restrictive modeling assumptions on the variational distribution, that means that if we start to sum up the number of variational parameters, then we have 2 times n times d variational parameters to learn. So d corresponding to the number of latent variables, 2 because we have these 2 guys up here, and we want to calculate a variational distribution for each of our data points. So that means that we have n in total of those. And that's sort of a bit problematic, that we have a number of variational parameters that increases that way with the number of data points that we have. Also, even if we learn a model, doing inference on new data points that come in can itself also be problematic, because the posterior distributions that we find for a data point is specific for that data point through its individual variational parameters. So trying to find a latent representation for a new test point here can itself be problematic. So what we will do instead, so our initial plan is replaced by a hopefully better plan, is to look into some of the modeling assumptions that we are making and trying to change the scope of the optimization setup a bit. So we have our decoder model that links the latent variable zi with the xi here. That is, if we assume that that is smooth, that means that if we assume that if zi and zj are close, according to some metric, then we also expect that our data points are close to, according to some measure that we want to use here. And using that sort of smoothness thing in terms of the decoder network, we would also expect that our variational parameters should be close. So if we have two data points that are close, xi and xj, then our variational parameters lambda I and lambda j, specific for these two data points, should also be close. So therefore, instead of defining latent or variational parameters for each of the data points, we will instead assume that there exists a smooth function that we'll call h that provides the latent, the variational parameters for the ith data point. So we assume that there is a neural network here, which we'll see, that takes xi as input and provides some variational parameters. And these variational parameters here then defines the variational distribution for that particular data point. This network here is also referred to as the encoder network. So we are encoding from the data space into the latent space. And the neat thing about this is that rather than having the number of latent, the variational parameter increase with the number of data points that we have, the parameters that we want to learn is defined by the weights or the parameters that goes into the neural network specification of our encoder model. So the number of parameters is fixed and not dependent on the number of data points that we get in. So that's our setup instead, our hopefully better plan that we have here. This type of inference, when we are changing our learning setup this way, is also called amortized inference. So we are learning a model of this type here that takes input and then provides variational parameters instead. And this is sort of a technique that's also applicable outside just variational autoencoders, but can be used more generally within when you're doing this type of inference and learning. So I already said that we are working with a fixed size vector, and sometimes we will abuse notation a bit and say that the parameters that goes into our encoder network, so the weights in our neural network, will also be, we'll use lambda to refer to these parameters here. So the parameters in the encoder network is, we'll use the same notation as when we're referring to our variational parameters, because the variational parameters are given directly from the encoder network. So the model stays the same, it's only a matter of the parameterization that is being changed. Yes. So now we have the full story here is that we have a model here where we again assume a prior distribution over our latent variables. We assume that the decoder network here is, provides lockets for our Bernoulli random variables observation down here that lives in our data space. And then we have a variational distribution that takes as input our data points and then provide, in this case here, a Gaussian distribution over our latent space where the mean and the covariance matrix that parameterizes, that's used to parameterize the distribution in the latent space are given by our encoder network H. And our learning objective now becomes optimizing, maximizing the elbow function down here with respect to both the weights that goes into the neural network representation of our encoder network and omega, that was these parameters that goes into the decoder network that we have specified in our model architecture up here. So that's sort of the twist that we put to our the type of variational setup that we have been discussing so far. We are moving it in this to this type of amortized inference setting where we are a bit more efficient in terms of the number of parameters that we actually need to learn when we learn based on data. So But otherwise, everything stays the same. So Helge also introduced sort of this cycle here for doing the learning. So we are still relying on gradient-based methods for doing the optimization. So we need to increase our evidence lower bound here. We make samples. We do that based on a sampling-based approach, whether it's the score function or the reparameterization approach. We calculate our gradients and we update both the parameters that goes into our model specification and the variational parameters, lambda, corresponding to the weights of our neural network encoder. And then we are simply iterating over this approach. So stepping a bit back, also taking into sort of the context of what we have been Silja has been discussing previously about Box's loop and what Helge has also been talking about in the beginning of today's lecture. We have this nice framework of, with, for instance, Pyro or generally probabilistic programming languages that helps us to avoid having to do a lot of, or to care about a lot of computational or model-specific details. So that means that, again, with all this setup here, the stuff that I described on the previous slide about doing these iterations and what we illustrated with Pyro previously, this is something, the computational details we do not need to take into account. Instead, we can focus on the part that really matters, specifying the model and potentially also specifying our variational distributions or our guides in this case here. And then trying to understand the data through the lens of the models that we have learned and try to revise the models based on the insights that we get. And this is just to illustrate a bit of that process. So here is a small example. We are going to set the scene of learning a variational autoencoder based on the MNIST data set, and you're going to play around with that shortly. So we have the MNIST data set with 50,000 training example over handwritten images, digits from 0 to 9. Each of the images or digits is being binarized so that we have either a pixel can either be on or off, and it's 28 by 28, these images, so we have in total 784 pixel values for each of the digits. In these examples that I'm going to show, we assume a very simple variational autoencoder with just two-dimensional latent space, and that's sort of mostly for visualization purposes. And we again assume that we have a Gaussian distribution on top of that, and that these two factors are the two latent factors or variables are independent of each other. We assume a encoder network like this, so we are encoding from the data space to the latent space. So we have an input from a 784-dimensional vector that is being mapped up to mapped down to a 256-dimensional latent representation or hidden representation, and then also applying a ReLU activation function. Then we are mapping down to 64 dimensions. Then we are branching out and calculating the log of the covariance matrix over our latent space and the mean value down here, and these two vectors that we get are used to parameterize our variational distribution. Here I'm also going to assume that the covariance matrix here is diagonal, so we only have in this case here it would consist of two entries, so we are assuming that the latent factors here are also independent in terms of its posterior distribution. For the decoder network, we map from our two-dimensional latent space to a 64-dimensional hidden space to a 256-dimensional space, and then down to our 784-dimensional space corresponding to each of the pixels. And the values that we have down here are interpreted as logits for Bernoulli distributions, one for each of these variables corresponding to pixels that we have in our image. And then just to show some results from this model here that we are going to play around with in a notebook later. And just again, a small disclaimer here that the results that you will see here are based on this very simple model with a simple encoder-decoder network and a very simple latent space, namely only two-dimensional here. But it's just to illustrate also this approach where we are trying to do incremental model evaluations and model refinements and investigating the models and seeing what that actually tells us. So what we can try to do, an example here, is to reconstruct images that we are after doing learning. So we have an image, we calculate its position in latent space, and here we are just taking the expected value in latent space. And then we are using this expected value here, we are mapping back down to the data space. And then what we try to see here is that we have the true value here is the data in the data space. We have a 2, we are mapping it to latent space and then back again, and we end up with a 3. Here we have a 3 and we end up with something that looks like a 3 also. And again, now I'm saying that it's a 3, this should be interpreted that it looks like a 3. And here we have a 4 that then maps down to something is being reconstructed as something that looks like a 9. And we have something similar here, a 0 that maps down to something that looks like an 8. So there's clearly something that's not really working here. And one of the problems can be that you could then ask yourself is, okay, maybe the latent space is not sufficiently expressive, not sufficiently large to actually accommodate the nuances that we have in the images. So what you can, for instance, see here is that we have 2 is being mapped to 3, 4 is being mapped to 9, also down here. And if we investigate the latent space a bit, so what we have done here is to take the latent space and then simply partitioning it into blocks. And it should be read so that we have equal probability mass in each of these areas here. And then we have sampled a value for each of the blocks positions in the latent space and calculated, going through the decoder network and calculated an expected image. And what you can see up here is that we have sort of 4 and 9s that appear up here. You have 2 and 3s down here, and you have 5 and 6s and so over here. So going back to the examples that I showed you before, we had sort of a confusion between 2 and 3, 4 and 9, just examples. And this sort of makes sense that we have up here when we look at the latent space, 4 and 9 appears together, so that could be sort of the cause for this confusion. 2 and 3 appears together down here, so maybe we need a more expressive latent space. We could also look at sort of the latent space, so in terms of the distributions, class-wise distributions. So what we have done here is to take the data points from the test set, mapping it into latent space, and then we have put on density curves for each of the classes. So we have 0s are living here, 6s are living here, 1s are living up here, and so forth. So you can also see here that we have quite a bit of an overlap between the different contour plots, indicating that we are working with, we don't have kind of separation that we would like to have in the latent space because of this overlap. So again, we might be looking for more sophisticated encoder-decoder networks, maybe a more complex latent space to get a better type of separability here. So this is some of the things that you should try to explore now for the last exercise session for today. So we have a VAE notebook on GitHub for you to play around with. In the beginning here, the first part here, we are just getting some data samples. And just to make things a bit speedy to start with, we are only looking at the digits 5, 6, and 7. And we are looking at 100 samples only. And we are, just as we did in the slides, we are binarizing everything. This is what is happening here. And that is basically it. And everything here is being selected randomly. So the images that we have are, for instance, 5 looking like this. Here we are defining sort of the overall architecture of our variational autoencoder. So it inherited from the PyTorch neural network module. It takes as input here the dimensionality of the latent space, an encoder and a decoder that is being assigned here, and we are going to specify them later on. So now we just assume that we have an encoder and a decoder network. Here we are specifying the model. So the model here takes the data points as input that we have. We register our decoder network here, and then we are defining defining sort of the model using the plate notation. So we have 100 data points, so our plate here would be over 100, have 100 elements in it. This part here defines the latent space. So here we are defining the latent variables, normally distributed with the location and the scale, and these are just initialized to zeros and ones respectively up here. We put it through the decoder network, and down here we have our observations, Bernoulli distributed, and they are given observations corresponding to our data that we've supplied as input up here. The guide is given here. Again, the decoder and the encoder are assumed given. That will be specified later. So again, we have here a plate over the data points that are provided. We are given, we put our input into the encoder network, and get a location and a scale for the latent space, and then we define a variable latent here, a normal distribution with these two, a latent, the location and the scale corresponding to the values that we've calculated. We register the encoder up here with Pyro or with PyTorch, indicating that the parameters of the decoder network is also being optimized during the learning in the same way as the parameters of our decoder network is being optimized. Then we have a bit of code here for sampling images. So given a position in latent space, we want to generate a few images. We are first generating the mean value of an image, and then a collection of images directly with thresholded values between black and white. Here we are reconstructing images, so we are moving from having an image, positioning it in, or mapping it to latent space, and then back again. So it's just for visualization purposes and not really part of the variational autoencoder. Here we are defining our encoder network, mapping from the data space to the latent space. We have a very simple architecture where we are putting it in through, we have a fully connected network that maps from 784 dimensional, our pixels, to a hidden dimension here that's fixed, and then we are passing it through a ReLU nonlinearity. Then we are mapping this hidden representation here through another neural network, providing us with a location and a scale that goes into, that defines our the parameters, the variational parameters for our latent distribution. And here we have a soft plus to ensure that the scale is positive. And our decoder here is even simpler. So we are justifying a linear decoder. So we just have a linear function here that maps from our latent space directly down to our data space. And that is, what is being provided here. What we get as output here are the lockets for the Bernoulli distributions defining the pixels of the image. And this is what we have. Now we can do training. Or we have a function for doing training, and now we perform the learning. We have 2 dimensions. We define our variational autoencoder here. 500 hidden layer with 500 of size 500. Learning rate 0.01. Number of epochs 1000, and then everything is more or less the same as you have seen before. And let's try to do learning. We're doing a bit of plotting on the way. So here we are trying to reiterate here, these are samples that we have generated 5 random images. And what we have down here are us trying to reconstruct these images here based on the parameters that we have at iteration 0. And everything here is just random because we haven't done any learning. After 500 iterations, things starts to improve a bit. So now we can see there's some resemblance between what we put in and what we get out of it. It's still pretty blurry, and things improve a bit here. It's still not terribly convincing. It's rather blurred images that we have here, but there are resemblances. We can look at the elbow here, and it behaves nicely. So we have sort of a rather steady increase. We may not have quite converged, but that's sort of a minor issue now. Then we can start to explore the latent space. And here we are taking the digits, our digits, and mapping it into latent space, also labeling also labeling the data points with the labels from the data. So we can see here that the 5s live up here, we have 7s living down here, and then we have 6s living over here. And we can also explore the latent space a bit more. So what we are doing here is to taking the 2 dimension that's defining the latent space, dividing it up into unit squares, and then transforming it back into latent space, ensuring that the regions that we have in our latent space from which we sample are giving equal probability mass. And then we are simply generating data points here. So what that means is that if we are looking at our latent space and picking a point here and mapping it down to our image space, then we get something weird looking like this. And as we move down here, then we get something that look maybe a bit slightly better. But really not very convincing as it is now. Yes, and that's precisely what we are coming to, and which you are also going to play around with in just a second. But you are spot on. So let me just show you the last plot here. This is sort of, again, a contour plot of where the data points live in the latent space. So one of the things to notice is that despite that we don't really see these reconstructions that we would like in terms of quality, there are also a few other things, so we can see that there's quite a bit of an overlap between the contour plots. But another thing to notice is that we are not really exploiting the latent space. Okay, the first dimension, okay, we are from -4 to 4, but if you notice dimension 2, we are only working from -6 or up to -1. So the latent space is not really coming into play. And this is probably also a result of this here, sort of a consequence of that, most likely. So you can see down here we have sort of images that we would expect to see, but up here it really looks garbled, and the colors are also inverted. But that would also correspond to part of the latent space that is not being used down here. So there's also something going wrong with the way that our encoder and decoder network allows us to use at least the representation that we are given, the 2 dimension that we are working with here. So what you'll be working with a bit now is, before we end for today, is try to improve on this. So we have made some code here for a fancy decoder and a fancy encoder that you can try to fill in. Maybe a good starting point would simply be to copy the code that is already given in the not so fancy encoder and decoder. And then we have all the code down here for doing the learning, plotting and comparison of the latent spaces. But this is sort of the part to fill in. The decoder network was the simplest one, so maybe that would be a focus point to start with, and then trying just to work with these 2-dimensional cases that you have. Okay, let's just spend a few minutes to wrap things up. So we didn't have that much time to play around with this exercise here, but I hope that we hope that you had at least some time just to get a better feel for it. just to illustrate a possible solution here. So what we have done is to, so you were given the template for the fancy decoder and the fancy encoder. And what we have done to come up with something more fancy is just to actually look at the slides and implement the encoder and decoder network that we have here. You can find the specifications of the models, the encoder and the decoder network here. And let's just run this, and we have our fancy encoder here. So again, no point in going through the code here because it's just one-to-one with the network specification that you had on the slides. And now we are ready to do the learning here. This code is basically the same as we had for when we work with the simpler encoder and the decoder. We are still working with a hidden, we have now two hidden layers, one with 256 dimensions, one with 64 dimensions, and it's sort of the same thing for the decoder. This was for the encoder part. The learning setup is otherwise the same. So we can start to do learning here. And now we got something sample that is actually rather difficult to recognize. So let's see what it comes up with. Okay, it's being sampled. Okay. So we have our results here. And we have something that is a bit more clear than what you had previously in terms of sort of when we are reconstructing our images. We have the elbows has still this nice behavior. We haven't converged yet, so it might be an idea to increase the number of iterations a bit. We can do an exploration of the latent space. And here we are doing, this here is from our simple model that we started out with. This here is for the new model, and what we can see is that we have a somewhat better separation. So we had here the orange and the blue were partly overlapping here. Except for a few points in here, they seem to be a bit better, well separated. We also had this issue about the latent space for our simple model, where we saw that the latent space was not really utilized. This here is what we get from our new model, where we see a much better utilization or clear picture being generated when we sample from the latent space, where we have the 6s living down here, 5s, we have 7s, and so forth. And again, we have only 5, 6, and 7. That's the only images or digits that we have here. And this is also visible when we look at the latent space, the plots here. So we have the first dimension, the second dimension, and you can see here we are working with a much broader range of the latent space here than compared to our first attempt, where we are restricted here, at least in the second dimension. And then we had the contour plots down here, but they tell basically the same story again. So that was sort of one possible solution. Maybe you can come up with an even better encoder decoder architecture and get some different results, but that's sort of the gist of it. But the solutions will be available for you to play around with. You can also increase the number of digits that you want to use, both in terms of number of samples, but also classes. And then next thing is just the conclusions for today. Helge?
Yes, I don't know, why don't you just do the conclusion since you're already talking, but anyway. Congratulations, guys, you were able to live through the Variational Inference Day. Every year this is the most condensed and the most tiring day, and now we have made it. We wanted to end with a small recap or summary for you in case someone asks what the hell is this about. Then just check these slides and then you can tell them. So we started with motivating this whole thing by saying that we would like to do Bayesian machine learning. And the key there is to represent uncertainty really carefully. So we want to use distributions for anything that is unobserved, in particular for the model. So we are explicitly representing the epistemic uncertainty through a distribution function, this P of theta given D. So that was our goal here. And then when that was hard to calculate, we defined variational inference. So what variational inference will do is to provide us with this approximation, the Q of theta. And that is selected specifically for the objective of the Kullback-Leibler. So we find the one that fits our true distribution the best, calculated as the Kullback-Leibler from the approximation to the target. And this is then giving us the elbow and all that jazz. We use the mean field to make a set of candidates that is easy to work with. And there is a problem here, which we have talked about a lot, the underestimation of the uncertainty. So we are finding a solution that is kind of working towards our goal, but isn't really completely capturing the full uncertainty that we have, so therefore not an optimal solution. Now, after having defined the variational inference, we first did the old school approach, the CAVI, where we are analytically optimizing the elbow one dimension at a time, and then finding the solution for that in a way that is guaranteed to converge, and is even guaranteed to converge to the, say, correct model when we are doing conjugate exponential family distributions. We did this manually, so we derived the updated equations by hand. There are tools available to do this also automatically within this class of conjugate exponential family distributions. So fairly restricted model class, but very efficient when it works. Black box is more than general, and the nifty thing here is that it ties in with the deep learning construction, so we can put statistical flavors kind of to our deep learning models, and therefore being able to broadly expand on the models that we can play with. And we saw that now with the variational autoencoder as a kind of a tiny little taster for that type of model classes. The main problem here is now that the calculations are unstable, and there might be variance to this. We saw some elbow plots that were smoothly improving, but also some that were all over the place, and making sure that you know the model has converged to its best possibility. That's kind of the thing here for black box variational inference. Then Thomas talked about probabilistic programming languages and how that is a very useful tool in the box cycle. So it helps us to focus on modeling, making things that we really believe in, instead of on doing, say, tedious pencil pushing or building models that we know are completely wrong. There are lots of tools here. We used Pyro. We could have used TensorFlow probability or Turing, which is the Julia result or package that is useful there. So then after the VI day, what next? This toolbox that we have been introducing here, the variational inference toolbox, is kind of maturing. So people can use this and feel fairly comfortable that it works. But there are still things to do. The way that we chose materials for you guys today was the plan for us that you should be able to read and understand all papers or most papers in ProbAI domain. So when they say that, okay, we use this elbow, then you know what that means and what it does not mean. And in that sense, we hope that we have given you a good starting point for reading and maybe also for writing your own papers. But before we close, we would like to ask you for a favor. As you have been forced to live through, this day here is really, really compact. And we argue every year which parts to take out, and we never agree, and therefore we never take anything out. And therefore, again, we don't get enough time for the notebooks. So when you get to do the feedback forms at the end of this week, we would like to ask you to tell us explicitly which parts here are of less importance for you guys. That might help us to actually be able to improve this for next year's attempt. Okay, and with that, I think we are done. So thank you for today, and I hope you have a good next of the week.